Today what we're going to talk about is characterizing DC servo motors, and this is specifically for brushed DC motors. These are similar to the motors we use in the controls lab, and they're pretty simple to understand and pretty simple to what they do. So when you're using a DC motor, one of the first things you're going to notice when you're using it is that it doesn't respond to very, very low voltages or low voltages. Some motors, depending on how cheap they are, how bad the bearings are, it takes a couple of volts for the motor to start to move. And so this characteristic is called deadband. And deadband simply means that the motor is dead despite having a non-zero voltage applied to its input terminals. And so the motor will just sit there and not move and not move and not move. And then all of a sudden will start to move. And so if I were to sketch what a deadband looks like, there's a picture of it on the next page also, but if I were to sketch it in terms of an input graph like we did in when we were doing describing functions, which is one of the reasons why we did describing functions, there is a voltage input, Vn, and the motor simply does not move, and this is the theta dot of the motor, and so the motor makes no motion. And then when I get to some threshold voltage, the motor will start to move, and it's usually pretty much similar in the reverse direction. And so the motor kind of sketches out a function like this, and what this means is that the voltage simply has to increase past this critical point before the motor will start to move. And as you can imagine, this might be a particular problem for motors in certain applications. This means that if your input voltage gets below a certain voltage, the motor will simply stop, and it's not going to stop necessarily where you want to be hit. So this is less of a concern when I'm trying to control the velocity of the motor or the theta dot, and more of a concern when I'm trying to control the position of the output shaft of the motor. So I want to go to a specific position and stop. As you can see, as the voltage got slow or small as I was approaching the position where I wanted to stop, the motor would simply stop moving, and I wouldn't be at the position that I wanted to be at when it stopped moving. And so for that reason, characterizing the deadband is very, very important when I'm using a motor in a closed loop application. So how do we estimate the deadband? And the simple method that I've described here is to apply a adjustable voltage to the motor until it starts to move. So what you want to do is hook the motor up to a reasonably voltage source that isn't going to limit its current. In other words, you don't want the current limit to fool you into thinking what the voltage is. So you don't want the little lights saying over current lights coming on or anything. You want enough. So there are several ways you can do this. Batteries are excellent because they typically they will supply a lot of current before they have a problem. Also, there are lap supplies that if you use ones, it'll go to a couple amps or something like that. For small motors, they'll typically work. But you just want to turn the voltage up until you see the shaft of the motor start to move. And then you record that voltage, and you do it several times in both directions, forward and reverse, until you can get an idea of what the deadband is. And you're going to want to find the maximum deadband, and you're going to want to use that as a deadband for your motor model. What we're doing is we're going to add a nonlinearity to that simple motor model, have that single pole and time constant and a gain. Now, I want you to become aware as you're doing anything in mechatronics, I want you to become aware, or anything in engineering, is that you're never going to be able to completely 100% accurately measure the deadband. You simply cannot do it. One of the things that has to happen to you as a design engineer is you've got to stop wanting exact models and things to be perfect and everything like that, because as I say in this lecture, you're dealing here with the harsh reality of hardware. It's simply never going to be perfect, and you can't make it perfect, and no one can afford to make it perfect. So the sooner you learn to kind of ignore that problem, kind of the happier you're going to be as an engineer. And compensating the deadband, your deadband looks something like this. And so it's the same picture that we drew on the other page. I've got some V in. This should be a theta dot. That would be better. And some V in, and it'll start to move, and it will respond to the voltage. So I've got theta m dot. How much would be a dot too? It's a bad day. Anyway, theta m dot, and so this slope will give you the motor constant, that ratio for whatever that slope is. And so, but I want to make this motor so that I can use it in position applications. I want to eliminate the deadband. This is particularly crucial for things like standing robots, the inverted pendulum type things, all those kind of things. Compensating this deadband is critical to actually getting something to work. And so what do? Well, I'm going to add in a nonlinearity, and this nonlinearity is going to exactly cancel that deadband. Okay, so if you look at this, what's happening here is I've got between here and here, I have no motion. So in front of this deadband, I'm going to make the voltage jump up to the voltage that will cause it to start moving. So as soon as I see a command or a voltage input into it that's positive, I jump up to A as my input into the next block. And so just to kind of sketch that briefly, I would put this compensation block right here, and it looks like this. Let me draw it in another color. Since I got this fancy thing, I might as well draw it in another color. Okay, so I put that in front, and now this is my new command coming in here, and then my motor will start to move if I get the deadband compensated correctly, very, very close to a low voltage. It will start to slowly start to move, and which is, it's just what you're shooting for there. Okay, so by putting this in there, I've shown you kind of a pseudocode implementation of this. All you have to do is, if the command is greater than 0, then I just add and make a new command, which is the command plus that offset voltage that I'm using to compensate the deadband. If it's less than 0, then I subtract that voltage. If it's just to be complete, if it's neither of those two greater, if it's exactly equal to 0, which doesn't happen very often, I just set the command equal to 0 and leave it at that. Okay, now I'll have a Simulink demo that I'll put up online to kind of show you how this works. So I will write that down there so I'll remind myself to do it. So that Simulink demo will show you kind of what a compensated deadband. There are some concerns about compensating deadbands. Obviously, if I don't put in a big enough voltage, then what can happen is the motor will do better at compensating the deadband, but all it does is just reduce the width of the deadband. So you'll have this instead of something that looks like this. So I'll reduce it if I don't compensate it well enough. But there's also the question, what if I overcompensate it? In other words, I jump up too high. This area is actually, people still argue and struggle with this. There are some things you can do, in particular in light of what we had, particularly in light of what we learned about describing functions. Instead of replacing it with a vertical jump like this, what you can do is put in a very, very high gain jump like that, and it tends to be a little more forgiving in terms of its describing functions or whether you're going to induce oscillation into the system. So that said, that's the easiest way to do this. If you're using any sort of position application where the actual position of the motor is what matters, you're going to want to compensate the deadband. Less so for systems that are using a constant velocity of some kind or something like that, or trying to control the velocity, because in general, if your velocity that you're commanding is outside of the deadband, the system will respond fine and there won't be a problem with that. Okay. So measuring the motor torque and back EMF constant, remember we've got those two constants. We've got KT And then K, I've named it about a million things, but K back EMF, we'll just name it a big thing today. K back EMF is equal to KT if I'm using a consistent set of units. And so torque constant and the back EMF constant are the same. Now there's a couple of things I can do in order to measure this. I do ask you this question, which is a good one for you to consider, is how would you approach this problem? Somebody comes to you and says, I need to measure the torque constant of this motor, what are you going to do? Well, a couple of things I've written down as possibilities here. One is I can apply a constant current and measure the output torque. So I can measure torque fairly easily with a scale. So literally what I could do is if I could apply a constant current to the motor, I could then have it push, put some sort of arm on it. So got the motor, got some sort of arm, and it's going to be pushing on a scale. And I could use that, whatever I measured, to determine what the torque was being produced by the motor. And I could then figure out what the torque constant was based on the current going into the motor. So that's one possibility. Another is to drive the motor, use the motor as a generator. This only works for brush DC motors, but I could drive the motor as a generator and then measure the voltage at a constant angular velocity. I could measure the voltage, and then I get V back EMF is just equal to KT times omega, and so I can measure it again. There's some other sort of bizarre ways you can measure this. One of them is you can hook it up as a generator, and then you can put some sort of moment arm on it, and you can, in this case I've got this being a lump of clay or Velcro, and you can drop the arm and then look at the voltage that it generates. And so it will generate a voltage over time. You can, if you remember, the voltage output is a constant times the velocity. So it's going to start, I'll just draw a little sketch of the voltage here. It's going to start out as at zero, obviously it's not moving. And as it starts to move, the velocity will go up, and then eventually it'll hit the stop and the velocity will go back to zero. Okay, so it turns out, interestingly enough, that if you know the two angles that you're going through, and you can get a graph of the voltage, that if you can count the area under the graph and divide it by the difference in angle that you've traveled through, that you can get a measurement of back EMF. This, by the way, there is an instrument that would do this for you called an integrating voltmeter. They're hard to find. You can build them fairly easily, but they're hard to find. And this would do it for you. It just integrates the voltage as you let it swing down. And so that's one of the ways that you can measure back EMF. Okay, now you need to measure everything else. I mean, you've got a bunch of stuff. Obviously, you've got an armature resistance right here. You've measured this. You've got inertia. And remember, when you're measuring this inertia, that the motor inertia alone won't do it. You have to hook it to whatever it's going to be driving to get the inertia. And then you've got some damping factors. So this is, of course, torque constant. And this is the armature resistance. Sorry for the tapping noise. And this is the load plus motor inertia. And this is damping factor, viscous damping. Okay, you can rewrite this into a time constant form where this is the time constant, this is the motor gain, K sub m, and put an m there so it'll be consistent. And so if I could measure, in this case, if I could measure R sub A, and I know the viscous damping factor, and I know the tau, and I can pretty much get everything else. And so let's take a look, measuring R sub A using an ohm meter. I'm going to place an ohm meter on the output shaft of the motor, and I will get a resistance measurement. Then I'm going to slowly turn and stop the motor, because if I am generating with the motor when it's moving, it's going to give me a bad reading, because the way ohm meters work is they apply a known current or voltage across the resistor, and if I'm generating a voltage, it's going to mess things up, because it's going to limit that current. And so if I turn and stop, and what I'm going to do is I'm going to try to find an average. You can average if you want, or I generally take the minimum. Now, are they all going to be the same at every position? No, it's dependent on brush position and stuff, and you're never going to get them the same. But taking the minimum is pretty safe, because that tells you that kind of gives you a max current thing. Okay. Now, if I can measure tau and K, I guess I have to have K too, but if I can measure tau, how would I measure tau? What are some approaches I could take? Well, I can hook this up and put a step voltage input to it into the motor, and I can observe the response. The response to the motor is, I'm going to look at 63% of until it gets to its max value, how long it takes to do that, and that will give me tau. Okay, this is time in seconds. Now, there's some issues with this, one of which is, how in the world am I going to tell when it's at its max speed, because I just put a voltage in and it started spinning. Okay, there's a couple of things you can do that are kind of fun. One of them is you can take your iPad camera and you can put on top of the motor, we'll look from the top, you can put some sort of tag or something like that, and you can film this in high speed, and you can watch this spin. And what you'll be able to see is, from position to position in high speed and measuring the angles, you'll be able to see how fast, or you'll be able to see when it reaches its maximum. You'll be able to see what speed it is at various times, and you can sketch the speed points, and you can draw the curve and determine the angle from there. Measuring K, I can do the same thing for measuring K. I can put in a known step voltage, watch what constant it goes to, and knowing the voltage and knowing the constant velocity, this by the way is theta dot and time, knowing the velocity, I can figure out what that motor constant is, and so I can completely define my model by doing that. Okay, I've decided what I'm going to do with these is they're going to be short, they're going to be on the subject. I'm not going to talk forever, and then I'm going to put up a discussion. If you've got questions about what we're doing or anything else, please ask me. Hopefully you all saw the announcement I put up on Canvas. I put up a couple, but I just put up a recent one. There is a push to have a small, simple medical ventilator designed. And if you're interested in that project, or would be interested in forming a team, and you're currently up to date in everything in the project you're doing, and would like to change to that, you could work on it till the end of the semester. Competition for that, it's a $200,000 competition, ends in a couple of weeks, so it'd have to be pretty fast. But take a look at that and see what you think. If you're interested, let me know and we'll talk about it. I've also contacted some friends of mine in the industry, and we'll see how they respond to it too, and might be able to set up a team with them. So anyway, we're going to call this good for today. Again, I try to answer emails pretty quickly, and I'll put up discussion groups and stuff, and we can get through this. So far, locked in my room talking to something is pretty much like my old age is going to be, so it's not that bad. So I'll talk to you later.